will talk about the last topic in this course. It is carriage control. So what is carriage control? So the carriage control concerns ensuring a collection of mobile sensors, or you can consider as mobile of robots. Then the robots must be put in a way that an area is completely covered by the robots, such as this plot in the left. So at least for each location in this area, so this is the area. So each location is at least covered by one robot. So for each robot, it has its own sensing range. Then let's look at the plot at the right-hand side. So in this case, the area is not completely covered because there's a hole in the middle, and every location in this hole is not covered by any of the robots based on its own sensing range. There are different approaches to solve the coverage problem. In this lecture, we will introduce the one based on Voronoi partition. For any areas, let's say we have given an area. For any area, we can partition this area by different set, okay? Let's say the whole area is omega. It's in planar space. It's in two-dimensional space. Then we partition each one as they say W1, W2, W3, W4, W5, and so on, okay? Then the union of the Wi will be the whole area of omega, and the intersection between any two sets is empty unless they share a border, okay? Unless they share a border, but we can consider this Wi, they are, let's say, the only, we here empty, we only mean their shared border, okay? It's not exactly empty. So for this cost function, we will think if we put, so let's Vi denote some, let's say we have n agent, So the n agent can partition this space in Vi, or Vi is based on its own sensing range. Then this is the cost function. We have n sensors from 1 to n. And so the Vi, they forms a Voronoi partition. Let's say V1. So the union V1, V2 until Vn, they cover the area omega. Then V1 in any Vi, Vj empty. Empty means they only share a borderline. So then Q represents any point in this region omega. Q could be any point. So then PQ means how important of the the point omega in this region. Maybe we can, you can think of like, let's say, the probability density function, okay? Then for each point, it has different value. Maybe for some point here, it's a value of 0.1, maybe another point have 0.5. So P just shows the importance of the Q in the region. Then we take the integral and over the region VI. So the Q here, it basically means some function, f will be some function. Then its function is the distance of the location xi. For example, if this is the region VI, then we have a point xi. Then for other region in Q, so what would be difference between xi to every point? Then we integrate this Q in this whole space. So even though we use single integral, but you know it's an area integration. Integral over the area. So to find the best location of all the sensors or robots in an area, then we need to minimize this function over x and v. So x need to be in the center of vi. So we need to find the center of vi. Then all the vi, they need to be, let's say, partition this whole space. Okay, so based on this rule, if some point, let's say we have this area, so this is xi, so this is xj. So we decide for each point q, then let's calculate it's close to xi or xj. Okay, if it's close to xi, this q belongs to vi. Maybe we can practice this vi and this vj. Okay. Then here we want to minimize the cost function both on x and v. Of course, when you move x, it will change the side of v. So when we want to minimize something, this is the objective function. So it's equivalent to say we can calculate the gradient because we can use the gradient descent algorithm. If we calculate the gradient of this function with respect to the location of robot I, then we can move because only this one with index I is related to the xi. So all the other ones are 0. So then we can move the partial xi inside to this function. Then you will see that it naturally has this distributed property. And here it only depends on the agent's location xi and its neighbors. Here neighbors basically mean when they partition the set vi and vj, only the neighbors if they share a common line for the partition. So we consider that the neighbors. So you can see here, this algorithm only depends on xi, and so vi will be, we need some boundary with the neighbors. So it's a distributed algorithm. Now let's look at the special case. Okay, so the nonlinear function f, q, the distance between Q and X will just be the distance, okay? The square of the distance will be the norm of Q minus X, then square. Then we can calculate for any point, let's give a region omega. Then for omega, then we can calculate the center of the omega by using this formula. So the numerator will be the Q, then times, you can think of this, this is kind of like a probability. So this Q, and what's the probability of Q? That should be PQ, that should be the mean. It's like the mean of the variable Q in this omega region. Then you normalize by integral of Q over the whole region. Then we calculate this, the center, or you can consider this as a mean. The center of this region, omega. So here is only one point, okay? So then we find the center of Q. Then this is omega. We denote center as C omega, okay? Then we can use the parallel axis theorem for if we want to evaluate, okay? If a given omega, if I want to evaluate this function, this for any point X, would be the distance between X and square of distance between X and Q for every Q in this region. Okay, we have this one, then we times the weight of the Q, then we integral in the whole region of Q. So then this one can be written as two parts. So the first part is not related to X. It will be, you can use the distance between Q and the center of the omega and PQ, DQ. And the second part, you can use this one. It's like the denominator, then times here is times the norm between X and the center square. So in this way, when we take the partial derivative of X, we can easily to see this is not related to X. So this is a constant term. So we can easily calculate the partial derivative. Then we can apply this rule, this parallel axis theorem to every agent. Okay, then we have I from 1 to n. So this will be the Q to the center. Then we have xi to the center of vi, the norm, the distance, a square, then this is a constant term. Okay. Once the vi is fixed, and this is also a constant term if vi is fixed, then we take partial derivative of this function, partial theta I. So we know this part is constant. Then this is a constant term. Okay, we can put it here. And this one we have 2 times x minus the center of vi. Okay, this will be the gradient direction. So then for the control design part, we can use x dot. Let's assume single integrated dynamics. We want to minimize this function. We just take the opposite direction of the gradient direction will be minus k. So xi minus the center of vi. So then k, we can pick anything greater than 0. Then every agent uses this algorithm. Then eventually they will find the best location to cover an area omega. So until this lecture, we finish all the formal lectures about this course.